Yeah. Yeah.
That got interesting.
Yeah, it was like nothing happens for so long, and then like, you know, in the course of a few minutes, the wall is down. It was like, ooh, the wall is so cool. And then it was like, you know, that little mission to get like that one little guy to show Circe, like what was the point of all that? Like that was never gonna work anyways. So like you risk the lives of the most important characters in the show. And you lose a dragon, and then the wall comes down because of that dragon that you lost. Like they literally
Stupidest thing I've ever seen.
Yeah, it was really bad. Really bad.
They get a C+ in military strategy.
But at least, you know, finally Jon Snow and Daenerys hooked up, so there's that.
No, they found out that
Yeah, they don't know though. So like we're not allowed to be grossed out by it because they don't know. Also, we've gone way beyond those sorts of taboos in this show. So like this is supposed to be, this is supposed to be like a lot less gross. Plus they're pretty, so it helps, right? So, okay. So, let's talk about capacitors. We only have 2 lectures to get through today, and they're relatively short lectures. I just want to introduce you to 2 new fun, emphasis on the fun, circuit components that are going to open up new horizons for us in our circuits. So, we've done a lot with resistors and circuits, but we've kind of squeezed everything we can out of those. So now we're going to move on to bigger and better circuit components. So capacitors have 2 terminals and are composed of 2 conductive surfaces separated by some distance. One surface has charge Q and the other minus Q. A capacitor stores energy in an electric field between the surfaces. A lot of times it's introduced as being 2 plates, and that is the circuit symbol that we use, is like 2 plates that are in parallel. But real capacitors are typically not constructed that way. So real capacitor is there's like foil that's wrapped around several times. There are lots of different varieties, but yeah, so we try to say surfaces instead of plates, but sometimes we're just going to say plates on accident. So let a capacitor with voltage V across it and charge Q be characterized by the parameter capacitance, C. Okay? So for a capacitor, like a resistor, there is a parameter that sort of describes its properties. And the capacitance is that for the capacitor. Where the constitutive equation is that the charge on one of the surfaces is equal to the capacitance times the voltage across the element. So this is equation number 01.13. The capacitance has derived SI unit farad, F, where a farad is, in more familiar units, an amp second per volt. Okay? So, I mean, it kind of is pretty obvious that it would need to have that unit if you look at how it converts a voltage, there's the volts cancel, to a charge. So a farad is actually quite a lot of capacitance. Most capacitors have capacitances best represented in microfarads, nanofarads, and picofarads. Okay? So small. What's pico? 10 to the minus 12. That's right. It's also the beginning of my last name. So that was also an acceptable answer. Great. So, the time derivative of the constitutive equation yields the voltage-current relationship. We're always looking for that voltage-current relationship for our circuit elements. For a resistor, it's whose law? Ohm's law. And it says that the voltage and the current are proportional with constant of proportionality, the resistance of the resistor, right? For a capacitor, this relationship is found by taking the time derivative of the constitutive equation, which is something that we're going to notice is a theme. The constitutive equation, if you take the derivative of it, time derivative of it, then you get the elemental equation that describes the VI relationship. And if we take the time derivative, what is dq dt? Current. Time rate of change of charge is what the current is defined as being. This side, C is a pretty good approximation for a capacitor, is that C is a constant. Okay, so we don't have to worry about that when we take the time derivative of that side. dV dt, we're going to leave it as dV dt because we want it in terms of voltage. So we're going to actually solve for dV dt when I represent it here. dV dt equals, then when we have to divide both sides by C, and dq dt is just I. So for any specific capacitor, instead of writing Ohm's law down for it, we would write this equation, which is the elemental equation. And we've got a time derivative here, right? It's new. So in our resistor equation, no time derivative showed up there. Now, in KCL, KVL, Kirchhoff's laws, they're just algebraic relationships, right? So this is our first time derivative in one of these equations we're going to use to construct the dynamic equations for a system. Resistors have only algebraic IV relationships, so circuits with only sources and resistors can be described by algebraic relationships. The dynamics of circuits with capacitors are described with differential equations of derivatives. And this is probably familiar to everyone who's been doing the homework to an extent. Actually, there's an, no wait, it's not till next week's homework.
Yeah, you didn't do that.
Dang. Okay, next week. So something to look forward to. Not a capacitor, but an inductor is in. But I think there are also capacitors in the homework too. So both. Okay, so capacitors allow us to build many new types of circuits. So we can do filtering, which we don't really have an understanding of what filtering is yet in this class, but the idea is that there are some frequencies that are part of a signal that we might want to get rid of. Okay, and in a filter, you can do that. You can.
Would that be the same as like with using a soundboard for microphones? Like when sound comes in, you want to block out some frequencies in the mix.
Right, right. So for instance, you might have some high frequency noise that you want to get rid of. You would do some filtering on the high frequency stuff and do a low pass filter or a notch filter where you have certain frequencies that pass through and others that are filtered out. And we're going to explore that in detail later on, but for now, we just know that this is an opportunity to start building circuits that can do that type of thing. Capacitors are used all the time in, even in very basic circuits for filtering something. Very useful. You see oftentimes a capacitor to ground. That's usually going to be a low pass filter, and it's filtering out high frequency stuff. Great. Energy storage is another thing we can do with them. They're also resonant circuits. So, for instance, those RFID card readers around. They have resonant circuits in them that are tuned to a specific frequency. Blocking, so you can block the DC component, which is actually a type of filtering. Bypassing, which draws an AC component to ground. So these are all things that we'll learn about more later, but for now we could just say, oh wow, look at all these new types of circuits that we'll be able to build. So capacitors come in a number of varieties, with those with the largest capacity and least expensive being electrolytic capacitors. And most common being ceramic capacitors. So you guys seen those little orange capacitors that look like this? Yeah, those are ceramic capacitors. Electrolytic ones are usually, I mean, there are lots of different varieties, but electrolytic ones look a little bit like a barrel.
One side is kind of flat, usually.
Sometimes it depends. So depends on the brand, really. But yeah, these ones So we're going to talk a little bit about polarity. So there are two functional varieties. So those are the two, ceramic versus electrolytic. Kind of give you an idea of, the types that you can buy. But functionally, they're different. The two different types are bipolar versus polarized. Sometimes bipolar is also just called unpolarized versus polarized. With circuit diagram symbols shown in figure 1.4. So back to the other page. A bipolar capacitor has just this symbol where there are two even lines, and a polarized capacitor has one that's curved. And I put the plus and minus signs on this one, the polarized capacitor, to denote the fact that a polarized capacitor is only supposed to have voltage drops in that direction. They're not meant to be used for a voltage that's going to reverse. And in fact, it's dangerous to use them in that way. So if you reverse the voltage, at best you might damage the capacitor. At worst, it might explode. Capacitors are the only electronic component that I think we're going to encounter that has a pretty reasonable chance of exploding. Capacitors explode. Good times. So yeah, try to be careful with them. I mean, as long as you're working with small voltage and current, they aren't too dangerous, but yeah, they can explode. And you can hear them. I mean, sometimes they'll just fail without like the casing coming off of them, but they'll you just hear them pop. Yeah. Or they'll just be damaged and they won't work well, which is actually the most annoying because you don't know, and then you're trying to use it and it's not working, and you think that you're screwing something up in the way you're building the circuit, but it's actually just a capacitor that's compromised. So polarized capacitors can have voltage drops across in only one direction, from the anode, which is denoted with the plus sign, to the cathode, which is denoted with the minus sign. Otherwise, they can be damaged or may explode. That was a key word that I put over here, explosion. Electrolytic capacitors are polarized, and ceramic capacitors are bipolar. So that's 99.99% of the time, that statement is true. There are some bipolar electrolytic capacitors, but it turns out that they're mostly just built by this trick here. So what if you need a high capacitance bipolar capacitor. So bipolar capacitors are the ceramic ones. They are relatively small capacitance, right? That was what we learned about them. Electrolytic ones have larger capacitance, ceramic ones have smaller capacitance. But what if you need a bipolar capacitor for a circuit that's going to have voltage dropping both ways across the capacitor, but you need to be high capacitance? So here's a trick. This one's like an obscure trick that I found on the internet, and then we tested it, and it really does work. Place identical high capacity polarized capacitors cathode to cathode. So put the negative terminals together. What results is effectively a bipolar capacitor with capacitance half that of one of the polarized capacitors. But half of a polarized capacitor's capacitance is much larger than a picofarad ceramic capacitor. So, and the electrolytic ones can go up to significant. I mean, you can get millifarad or even farad capacitors that are electrolytic, but not ceramic ones. So, yeah, so it's a nice little trick there. So I decided to put it in the notes so that in case you guys ever encountered that possibility. Yeah.
How come one of those ones wouldn't explode?
It takes a pretty careful analysis of how the voltage drops work across those capacitors that are back to back. But essentially, when you put them back to back, they never have that reverse bias, the reverse voltage on them if you do it that way, which is a little bit non-obvious until you look at all the particulars of how it's connected. But it's a pretty neat trick. It was funny because some students were trying to find a large capacitance bipolar capacitor for doing some filtering with. And yeah, it was like we couldn't find anything that you could get off the shelf, so we were like, how could we construct one? And that, it turns out, is the easiest way to do it. So that's pretty cool. I thought that was a neat trick. Oh yeah, so for these, typically the cathode will have a stripe on the side, and it will have a shorter lead. So this is the minus side usually, and this is the plus side. And sometimes you'll also get these nice little like minus signs that look like, it looks like a highway where, you know, pass with care, that kind of thing. Those are minus signs on the side. And then these ones are bipolar, so they don't have that polarity to them. Okay, so any questions on capacitors?